Thank you very much. Thank you very much. Yeah, and it's my great pleasure to present here today. And my name is Xianghao Zhan and come from Department of Bioengineering at Stanford University. I'm the third year PhD here. And this work has also been done in collaboration with Fanjing Wang, who is from the Department of Pharmaceutics at University College London, and my PI Olivier Tivard at Department of Biomedical Data Science at Stanford University. So the title of this project is to filter drug-induced liver injury, which we refer to abbreviated as DILI, to filter the DILI literature with natural language processing and ensemble learning. And this project centers on the drug-induced liver injury. The reason why we would like to look into the drug-induced liver injury is that it has been a killer for almost the majority of the novel drug candidates. Firstly, the definition of drug-induced liver injury is generally defined as the unexpected adverse reaction to drugs. And DILI, the unexpected DILI, could cause acute liver failure and even death, because liver plays a key role in the metabolism of the drugs and also the antibiotics. So the unexpected delay could really lead to a fatal consequence. And it is because of the unexpected delay that many of the new drugs or drug candidates had never entered the clinical trials. Therefore, if we could better predict and diagnose delay, as it could be easier, it could be also very helpful for the new drug discovery for new drugs. In this case, we would like to try to develop a machine learning or AI tool to fast filter and try to detect daily literature. The reason is that the drug-induced liver injury results or experiments with drugs or chemicals are generally listed in a kind of publication format, in the free text format. So in that manner, the researchers have to find and look into this kind of manuscripts, look into the publication, and find out the results, whether this paper is related to DILI or not, and find out the exact chemicals that have positive or negative DILI effect. And in this manner, so this can takes a long time because it requires a manual reading of all the manuscripts on the PubMed, for instance. And so we are thinking of developing the NLP, the natural language processing tools, to classify the daily positive papers and also filter out the daily negative paper which are not related to drug-induced liver injury for potentially even faster processing of the potential drug candidates. So the ideal application of this kind of model should be kind of pumping up new publications and firstly filter the publications which are DILI positive, which are related to DILI, and then pop up to the researchers in this field. So in that case, it could improve the efficiency of the DILI prediction and DILI result finding process. And the dataset we use, which is also released by the CAMDA challenge this year, includes the PubMed papers, with both the daily positive papers and the papers which are not related to the drug-induced liver injury, and which we refer to as the daily negatives. They may come from other fields of biomedical researchers. And these kind of data is firstly being curated by FDA experts. And for the daily positive cases, there was about 14,000 samples. And for the daily negative, which are unrelated papers, there were also around 14,000 papers. But in the modeling process, only 50% of the data of the positive and negative cases has been released. In that manner, the other 50% has been held out for the testing or the validation of the model to evaluate the model performances. The data are in the format of this CSV file with title and or abstract. So not all publications are with both title and abstract. Some of them have the abstract. And the data, after releasing the data for the training purposes, there have also been more data has been used as a holdout validation set. The first holdout validation set include 14,211 samples with labels marks that are used to evaluate model performances, which are just as in a similar format as in the training dataset that has been released. And there was another additional holdout validation set with 2,000 samples with abstract only. So this small sample size of validation set is trying to evaluate model performances in the extreme cases where there are only abstract available. So here is one screenshot and snapshot of the example data sets we can use. As you can see, have the PubMed ID, the title, and the abstract. So after we got the data, first thing we need to do is to clean the data. We firstly pre-process the data by firstly partitioning the release data set into 80% training data and 20% validation data. So here, the 20% validation data are the data with labels that we are able to find. We know the labels that we can use this kind of 20% validation data to train the hyperparameters or to do model selection. It's like we can make use of the performance of this 20% validation data. And after we partition the entire data set into the training data and validation data, we perform the lower case, which we changed all the tags. As you can see in the previous one, there are the capitalized letter, and we just changed them to lowercase to make them normalized. And then we remove the punctuation, the numerics, the URLs, also the stop words such as the and, the, and this kind of words. And finally, we've also performed stemming by changing each word to their word stem. So by doing stemming, we can reduce the number of dimensionality of the feature space for some of the word vectorization approaches we used. But stemming is not required as the modeling process, so we deem the stemming as a hyperparameter or that will be tuned in our model selection process based on the feedback of the performance on the 20% validation data. And the data pre-processing part was done in Python and also the package with Jensen. So in that case, we can perform all these kind of cases with coding. And after we pre-process the text, it is still in the free text format, right? So what we need to do is one key step in NLP is try to converge the free text format language into kind of vectorized or the numerical value in a feature space. So the second step we are going to do is perform text vectorization. Here we use two different types to generate different types of text vectorization. The first one is the word-based text vectorization, and the second one is the language modeling-based vectorization. And here for the word-based text vectorization, we employed the backup words, the TF-IDF, the Wordtoback Models, and here the backup words is simply using the word count, which means that it uses the leverage the frequency of the term that appears in a document as the feature. And in this case, also the feature dimensionality is determined by all the distinct terms that appears in all documents. And for the TF-IDF, it is a kind of normalized version of the backup words. It normalizes the word count by not only taking into consideration the frequency of the terms, but also divide the frequency by the frequency of the document that contains this specific term. So in this case, the TF-IDF can focus more on the rare words that appears in a specific document. And the third one is Wordtoback model. It leverages the simple two-layer neural network and trying to optimize the embedding matrix of each of the documents or each of the terms. So by doing some simple works of predicting the center word given a surrounding words or predicting surrounding word given center words. So in this case, with this task, Word2Vect is able to optimize the embedding matrices by fixing the connecting weight of the neural network via the backpropagation. And here we directly use two pre-trained biomedical Wordtoback model that has been trained by different researchers. And I'm going to introduce these two Wordtoback model later in the next slide. And beside these three models, we have also used the language modeling-based vectorization, the pre-trained biomedical Centivac model, which has been trained on the PubMed and Mimic3 dataset. It encodes a document into 700 dimensionality feature space. So in this case, a document could be directly just converted into the numerical features on the 700 dimensional feature space. For the two Wordtoback model we use, they are pre-trained on different dataset. Firstly, the Wordtoback model 1, it has been trained on the PubMed, the PMC, and Wikipedia dataset. It encoded 16 million terms, and the terms has been encoded in a 200 dimensional feature space. And here is a link to where we downloaded the Wordtoback model, the word vectors. And the second Wordtoback model we refer to as Wordtoback model 2, and that is trained on PubMed data and the Mimic3 dataset. It includes 16 million terms and also encoded these terms into 200 dimensional feature space, and it is published in 2019. With these kind of text vectorization approaches, we can convert and transfer the free text format language into the numerically expressed or numerical feature space. So after doing the vectorization, we could see that we could perform a kind of data visualization with TISNI. So in that case, we could reduce the dimensionality with this TISNI as a nonlinear dimensionality reduction approach and visualize the data distribution on the two-dimensional feature space. Here, we use two examples of the TF-IDF and biomedical Centivac model as examples. Here, we could see the visualized result indicate that generally the DILI positive papers and DILI negative papers cluster together into two different general clusters that are dominated by different categories, which means the negative and positive cases can be separable. So in this case, this visualization is unsupervised, and this indicates that there is a feasibility that we could do the classification and prediction of the DILI positive and DILI negative papers by building models. So after we performed the vectorization, what we could do is the modeling. So we are going to perform the classification modeling. Here we are going to do 4 steps. Firstly, we have developed separate models trained on different word vectorization models. And then we developed the ensemble learning model that aggregates the information and knowledge of different separate learners. And the third one will perform the error analysis and finally interpret the models by interpreting the contributions of different separate learners in the ensemble learning process, and also what are the key factors driving the decision for the TF-IDF models. Here, before I introducing the specific modeling process, I'll firstly introduce you to these two different pipelines or protocols for modeling. Firstly, for the development of separate models without ensemble learning, which we directly develop models based on the word vectors based on different vectorization approaches, we directly use the 80% training data to train the models and test their performances on the 20% validation dataset. And for the development of the ensemble learning model, we further partitioned the training data, the 80% training data, into 2 sets. So after this additional dataset partitioning, here we could see that the dataset, entire release dataset, has been partitioned into 60% training data, 20% data for training the meta learner, and 20% of the data for the model validation. Here, we use the 60% of the data to train the separate learners and use the 20% of data to train a logistic regression that built upon the predicted probability of the separate learners. So in this case, it's 20% of data. With this 20% of the data, we're actually doing a data fusion on the decision level by making use of the predicted probability that are given by the separate learner be built upon different word vectorization approaches. And the details will be introduced later after we introduce the results one by one. So firstly, for the development of separate models, where we use the 80% of the data to train the models and 20% of the data to add the validation set to evaluate the model performances. For the model hyperparameters, which means the strengths of the L2 penalty in the logistic regression model we use, here we perform the five-fold cross-validation on the 80% training data for the hyperparameter tuning. And here we could see that we listed the model performance metrics in of these 5 different vectorizers. And we could see that the TF-IDF outperformed the other vectorizers with the highest AU-ROC, the area under the receiver operating characteristic curve, the highest accuracy, the higher area under the precision recall curve, the AU-PRC, and also the highest F1 score. And generally, the biomedical center vect ranked the second when compared with other methods. And it is also seen here, the backup words, which is kind of the conventional version of TF-IDF, generally is outperformed by TF-IDF. So because they are of similar origins, they are all based on word counts, and TF-IDF do further normalization. And therefore, in the future development of ensemble learning model, we will simply discard the most conventional and simplest backup words model and directly use these four vectorizers, TF-IDF, two word-to-vec model, and one center-vec model to develop the ensemble learning model. And the major motivation for the ensemble learning model based on the results on the separate learning is that we can see this kind of divergence across different separate learners after we analyze the false positives and false negatives of the result. We could see that although there are overlaps between these different models in their false positive predictions and false negative predictions, there are also huge divergence across different models. For example, here in the circle in purple, which is the currently best separate learner, the TF-IDF, and the second best separate learner, the center-vec model, you can see that there are huge predictions, a huge number of predictions that they are not overlapping, for instance, here and here. And in that case, there is huge divergence across different separate learners, which means their knowledge towards the decision are different in this kind of process. And their decision made by these different separate learners are also different. This kind of divergence could indicate that if we could make use of the knowledge from the different separate learners, it is possible for us to further improve the models. And here, that leads to our ensemble learning process, the development of separate class-weighted model first. So we use the four different vectorizers, the TF-IDF, the Wordtoback model, and center-vec model. And we firstly train the logistic regression models on each of them, and then aggregate the models in the meta learner, which is trained on the 20% of the data. Here, we added 3 different weight ratios to these specific models, which means we add different ratios to attend to the positive cases. The reason to do that is that we assume that in the real world cases, the number of or the prevalence of the DILI positive papers should be far fewer or far smaller when compared with the other papers that are unrelated to DILI. Therefore, we want our models to generally attend to the DILI positive cases and weigh more towards the positive predictions. Therefore, we added 3 different levels of weight ratios in the modeling, in the logistic regression modeling process. and added the L2 penalty to the model as well. And the L2 penalty was tuned in a file for cross-validation on the L2 penalty for the specific separate learners are tuned on the 60% training data, which are meant for the training for the separate learners, while the L2 penalty for the meta learner are tuned on the 20% data that is used to train the meta learner. Here is a list of the 12 different vectorization models we used to develop these meta learner. So as a result, we use the 12 different 12 data, the 60% of the training data to train the 12 different separate learners and use 20% of data to train the meta learner. And the L2 penalty was also tuned on the meta learner. Here we added the results of the ensemble learning model to the entire table. Here we could see that the ensemble learning models generally perform similarly to the previously best performing TF-IDF model with the same accuracy, AUPRC, and F1 score, and similar AU-ROC score. And after we visualize the area under the receiver operating characteristic curves and precision recall curves, we could generally see that the orange curve, which indicated TF-IDF performance, and also the brown curve, which indicates the ensemble learning model, are generally performing the best in these two metrics. But although this model showed almost the same performance on the validation sets which are partitioned by our own modeling process, and they are all from the release dataset, their performance on the holdout sets are quite different. Here we show the results on the two holdout datasets. So the holdout dataset 1 includes around 14,000 data points that include both the title and or the abstract, and the additional holdout dataset, which include 2,000 abstracts, which are labeled 2. Here, we could see that on the holdout dataset 1, we could generally see that the ensemble learning models are generally performing better than TF-IDF model with higher F1 score and higher precision, while on the second one, which is the additional holdout dataset, the TF-IDF model generally outperformed ensemble learning models with higher accuracy, F1 score, and precision. As for the reasons, we are hypothesizing that for the second dataset that only includes the abstract, which can actually give us more information. And the TF-IDF model is quite built upon the high dimensionality of the feature space because they are word-based. So the dimensionality is the same as the number of distinct words that encounter in the entire corpus. So if we could give the model more information, such as giving the model the direct abstract of the paper, actually we are making use of the ability of leveraging even more information in the TF-IDF models. And for the ensemble learning model, that includes both not only the TF-IDF model, but also the Wordtoback model, Stanford model, that actually takes more information from the prior knowledge that has been encoded into the Wordtoback model and the Stanford model that are learned from the general text environment. So generally, we hypothesize that the TF-IDF model perform better when we are giving more information from the abstract, when we could encode the data into the TF-IDF vectorizations. But generally, these two models perform well in terms of the performing metrics on the validation data, and it should be very interesting and very adjustable if the users want to use TF-IDF or ensemble learning models, as we further try to understand the specific performances of the TF-IDF model and the ensemble learning model by printing out and also plotting the confusion matrices. Here we plotted the confusion matrices of the different model on the 20% validation data where we know the exact labels. And here on the first row, the backup words, TF-IDF, the Wordtoback model 1. And on the second row, they are Wordtoback Model 2, the Sensovac model, and Ensemble learning model. So the general highlight here is that for the TF model, it has the fewest false positive predictions. Well, for the ensemble learning model, it has the fewest false negative predictions. Well, here I think we could have a kind of thinking and think of this kind of scenario, whether the false positive or the false negative, which one matter more. Well, from my perspective, I think the false negative rate is actually more important than the false positive rate, because imagine the scenario that we're going to use this kind of model. It could be kind of filter of the DILI literature. For instance, every day there may be thousands of new publications, and this DILI filter could filter the publication and pump the related publications to the researchers of drug discovery. And here, if the DILI filter missed one publication that could be really troublesome, they could be problematic, and they could miss some of the positive cases. So, but if it's just false positive, after we label that, after DILI filter label that to be positive, generally the users, the DILI researchers, could still read through this manuscript and filter them out by manually. So in this case, a high false positive rate generally just means the lower efficiency of the model, but it means that generally there is still the key DILI related papers are still kept there. But if a DILI positive cases is mislabeled as DILI negative, that means that the information related to that publication is totally lost. So I think, so generally we hypothesize that the false negative rate matters more. So generally, for the users who care more about the false negative rate in the DILI filter, the ensemble learning may be preferred when compared with the TF-IDMF model, although both of them are performing well on our validation datasets. So after we perform the error analysis, we move further to interpret the model, because this is one of the major advantage of of the models we use in this study, because the models we use are mostly, for instance, based on words or based on logistic regression. And so in that case, we could simply interpret the importance of their contributions of the words, or importance of the by the contributions of different separate learners, by interpreting the different logistic regression coefficients. Here, we directly do that. We bootstrap the 80% training data for 1,000 times, and in each time, we just computed the coefficient in the logistic regression for the TF model. And finally, we ranked the important words by their mean coefficient in the logistic regression. So in this case, we filtered and also shown the top 10 words that are related to the positive predictions and top 10 words related to the negative predictions. And here we could generally see that for the top 10 words related to the positive cases, which are the positive, there are words such as safety, hepatotox, liver, hepatotoxic, efficacy, and placebo, adverse drugs. So these words are all in their standard version. So these are clearly related to the drug-induced liver injury researchers. For instance, safety, the hepatotox, which is the stand for the hepatotoxicity, and liver and hepat. So this generally shows the meaningful decision given by the TF-IDF. And on the other end, we can see that for the important words related to the negative predictions, there are words such as perform, the mice radiate procedure, cell, express, vaccine, and rats. So generally, we assume that these words are more related to the other field of biomedical researches, which are not related to drug-induced liver injury. So in that case, we could see that by interpreting the important words in TF-IDF, we could see the model interpretability of the model used in the study. And by using a kind of similar pattern of interpreting the coefficient of logistic regression, we could also see the contributions of different separate learners in the meta learners in the ensemble learning process. Here, we bootstrap the 20% meta learner training data for 2,000 times, and with these 12 different separate learners, we show their coefficient distribution here. And the number 1 to number 3 indicate the TF-NF model, 4 to 9 indicates the Wordtoback model from these two different Wordtoback models, and the last three, 10 to 12, they indicate the Ensemble model. So generally, we could see that the highest contributions are from the TF-NF model and the Ensemble model, which also corresponded well with our result that the TF-NF model and biomedical Ensemble model are ranking the top two in our performance metrics. And what is also interesting is that the Wordtoback models, although they are contributing less, their contribution is still above zero. So that generally showing that all these 4 different types of vectorization models and all these 12 different models are contributing towards the same direction in making the final prediction given by the ensemble learning model. So to sum up, what we have done in this study is try to use the NLP, the natural language processing tools, the text vectorization approaches, to develop the prediction models of drug-induced liver injury. And the application of this tool will be to enable the researchers in drug discovery to filter the DILI literature without the time-consuming manual work to read through this manuscript one by one. Yeah, but there are still some limitations that could be could be done in the future. For instance, in this study, we only use the conventional natural language processing text vectorization approaches, and we did not try out the large pre-trained language models. And in the future, the large pre-trained language models such as the BERT or the clinical BERT, and also the Transformer XL could be used. But yeah, the margin, and I think so far given by this study, which has already shown high performance of this data, the margin of improvement could be limited. So this is also one of the reasons that we do not think or we do not need to test out this kind of pre-trained language models on this small data set. And in the future, more studies could be done on these pre-trained language models to see whether we could get further improvements, even we already got a high accuracy and high IUROC in this application. And finally, I would like to express my gratitude to my collaborator, Fanjin Wang from UCL, and my PI, Olivia Chivard from Stanford Biomedical Data Science. So that's all of the presentations, and thank you very much for the privilege of your time.
Thank you for a very nice presentation. Okay, so there are some already questions in the Q&A, but maybe before we'll go to those questions, I mean, people can still add them. But before we go to those questions, I also will have maybe one comment, one question, just in hot. When you were saying about the balancing or maybe not balancing between false negatives and false positives, and you think that the false negatives is it's better to focus on and to limit those in this application, uh, I think it's, I mean, especially for this use case when we would rather don't want to miss anything, right? To be able to do not miss any bad effect. I think this is the right direction. So I would argue the same way that if I have to pick between false negatives and false positives, then in this application I would rather go with limiting the false negatives. And the question, which in fact is discussed with the other organizers also of the CAMDA, is that how you think it should be done, the addressing of the unbalanced nature of this pairs through DD papers in the overall corpus, because of course what we are providing here, it's a bit artificial. But what do you think, how to deal with this unbalance, the space?
Oh, thank you very much for the question. Well, So for the unbalancing, so what we have done in this study is try to add in different weights, but generally, it would be awesome, yeah, if we could, for instance, provide the users or provide the contestants with a data set that more better resemble the real world cases. For instance, the prevalence could be low. Yeah, for instance, if there are, for instance, if after reading 10 papers, there are only one paper related to DILI positive cases in the general publication field.
Mhm.
So probably we could give out the data set that is only 1%, only, sorry, it should be 10% positive DILI positive cases and 90% unrelated papers. So in that case, the metrics of the area and the precision recall curves can matter more
Yep.
generally, because yeah, in that case, yeah, the prevalence is low, and to simply using the AUROC is not enough to reflect to drive the model selection process. So generally, to deal with this thing, I think firstly we should look at the AUPRC, and secondly, we can try to weigh differently in the modeling process in the loss function. Yeah.
Okay, so maybe I will now read the questions from the Q&A, because if it's recording, I don't know whether in recording people will see what was written on Q&A. So one question from Vitold. So the person who's in fact involved in preparing the challenge is, did you check what do different models contribute to the ensemble? Like, are there some aspects of the papers that some models are better in recognizing than others?
What do different models contribute to the ensemble? Oh, thank you very much for this question first. Yeah, it's really good question. So in the study, our interpretation of ensemble learning models are purely based on the logistic regression coefficient, which when we aggregate the decisions. So the step is like firstly making a prediction for each separate learners, and then aggregate their predicted probability in the decision level. So actually, when they reach this decision level, what we are aggregating are simply the predicted probability. And here we could see that only 20% data to train the meta learners, the contributions are shown that the TF-IDF and the biomedical central vect are the most contributing most. So this generally means that their predictions better correlate with the general labels, with the labels in the 20% data used to train the meta learners. So generally the dominant cases should be the TF-IDF and central-back models. Yeah. So, but for the exact knowledge that to be learned, we could not deduce simply based on the predicted probability or the logistic regression model on the top of the predicted probability. Yeah.
Okay, so you see the probabilities which are then plugged in from different models, but you cannot really aggregate it towards some meta features. I mean, which model is doing with what? Okay. Okay. Then there was the other questions. So I think, yeah, let's from Alina's three questions maybe start from the bottom, because I think this was the first one. So Alina missed the first few slides. What's the language you use to implement the tool? I think it was
Uh,
on your slides, but on the beginning, but I think Alina has missed those.
oh yeah, yeah. So the language is in English. Yeah.
Okay. And then there you have a question: why RAD is a negative predictor? Uh,
Yeah, I
because
think this is quite interesting. Yeah, I also find it quite interesting. I think probably this depends on the prevalence of this data set when we are analyzing the words. I think, yeah, for instance, because it's TF-IDF model, yeah, and generally it focused on the rats may appear, of course, it may appear in the daily papers, but they may actually appear more in other papers, because the TF-IDF can actually normalize the actual number of the documents that contain the word rat. So yeah, if this work is related to, for instance, epidemiology, or not epidemiology, but epigenetics, the work is all this work is related to gene editing. I think most of the biomedical work, most of the fields that are different from the DILI papers, they may be the rats may appear even more. Yeah, so that's the cases. I think probably the model attend to that and find that the rat may be more likely to get related to other field or DILI
Mhm.
negative. Yeah.
I think it would be interesting topic to further discuss with the toxicogenomic people because the rat is used, but as far as I know, in terms of the toxicity, it's a bit more sensitive than human. So maybe it also might have an effect because this translation of the effect from the rat to human, it's not one to one. But I'm not an expert here. Okay, and the last question from Marina was: have you tried to investigate why the holdout data 2 is harder to predict?
Hey, thank you very much for this great question. Yeah, because the reason I think we cannot answer this question directly is that we do not know the labels. Yeah, we do not know the labels of this holdout data set. They are holdout. Yeah, so we cannot understand the performance by doing error analysis. So, but generally, why it is harder to predict? Yeah, I think probably it is different distribution because generally, if for the training data, I think most of them have titles, and the second thing is that probably the prevalence in data set two may be different. Yeah, so yeah, only have 2,000 abstracts, and yeah, that's the reason I guess. Yeah, why data set two is harder to predict. But I think Pavel, you probably have a better understanding, and you may answer this question.
I think it might. Eventually, Alina will write again. But going back to the question about the language, she was asking about the programming language. I mean, which you are using. I think you put the Python right on the slides.
Oh yeah. The coding is language is in
The coding
Python.
in
Yeah,
Python,
yeah,
right?
yeah.